All right, let's go on to part two of lecture six. Um, we're going to continue with matrix transformation. I am Professor Wu, and this is Northeastern University. Okay, so I think last class we're talking about transforming vectors into like rotation, multiplied by one, multiplied by zero. Um, so I think last time we talked about averaging. So if you remember, if you multiply a vector by the one vector, right, then it's just going to essentially sum up every value. Now, after you sum up every value, right, you can also take the average. So after you sum it up, if you were to add the 1 over n, so depending on the size of the vector, if it's 3, then it's 1 over 3. So what's happening here is you take the vector, you're averaging it together, and then you divide by 3. So when you average them, when you add them up and divide by 3, that's equivalent to averaging. Right? Here you have multiple vectors, so you're going to find the average of this, and this. Okay, so the average of the first one is just 2, 3. Second one is 5 over 3, and the third one is 1 over 3. So you can find the average of multiple points simultaneously by multiplying the matrix by by the averaging matrix. So, like I said, the difference between moving a point and moving an object. Here, we're not no longer just moving a point. We're moving every single point. And together, all the points together form an object. Here, it's a stick figure, right? So the way um, we would like to move multiple points is to let's say we want to move a vector. Okay, so let's start with a vector. And we want to move this vector to this point. And the way we could do that is essentially just add the vector to some value. And the vector is 1, 2. We add to this value, and you give us 3, 3. So that's one point. Now, if you want to move multiple points simultaneously, okay, by you want to move by this much. Remember the 2, 1. We want to move by 2, 1. Okay, and now we have multiple points: x1, x2, x3, x4, x5, x6, x7. The way I told you previously is that you can stack them up vertically. So instead of just one, now you have multiple of them. And if you were to draw these out, these are the points of the stick figure. This one here. And if we want to perform, we want to add this to this. Well, the dimension has to match. So the way you could do it is you take this, which is how much you want to move by, and multiply it by the one vector. Once you do this outer product, then it becomes like this. So you essentially copy this 7 times, right? Once you copy this 7 times, the dimensions are exactly the same. So you can then add them together. And once you've done that, you essentially have transformed this to here. So we took this and add them together. I think I may have done something wrong. Yeah, I think this addition that doesn't correspond to this. It moves it this way, 2 by 1. So I think it's going to end up here. Yeah, yeah, you'll end up like somewhere here. Anyway, so this is probably not right. Okay, so if you want to combine multiple transformations, So remember, if you have like a rotation, right, theta, so you can rotate it, but you can rotate it again, theta 2. So this is rotating it twice, and then you can multiply by some other matrix. What other matrix do we do? Yeah, permutation. And then we can multiply by permutation, right? So you can do it one stage. Once you transformed it, you can transform again, then you can transform again. Now, these transformation, if you remember matrix multiplication, you can multiply all of them together. So if you multiply P, R, and R together, you just becomes a new matrix. So you can perform the transformation with just one multiplication, the Q. Okay, so when you combine multiple, so let's say here we want to rotate a vector, right? We're gonna and scale it by 2. So this matrix is scaled by 2, and this matrix is multiplication. This means that we can combine the two of them, which becomes like this, and we just multiply it once, and it will automatically rotate and scale for us. Huh. So here is an example of a permutation, right? We basically scale it and then we permute. So if we just scale it, it would be 2, 4. But the permutation moves 4 up and 2 down. And therefore, if I had multiplied the two matrices together, it would become this. Notice if I just take my vector, multiply this, I get the same thing. So multiplying a whole bunch of transformations together ahead of time is a compact way of essentially knowing how to directly jump to the final transformation. Okay, next we're going to talk about how to center data. So if we have the stick figure, for example, the the center point of the stick figure, if we find the average point, so all the average x's, all the average y's is here. A very important transformation is the movement of this thing, the entire stick figure, so it's centered at 0. So you're like right in the middle. Here's 0, right? Well, the way to do this is essentially, um, well, first you have to. So you have two dimensions. So you want to find the average of dimension 1 and the average of dimension 2. That will give us this point essentially. Once you find the average, which is roughly 3, 1.4, right? 3 and 1.4 right here. So once you found the average, if you subtract, if you take the original points and subtract the average, you are going to move this to the center so that its center is around 0, 0. Now, notice what I did is here's X, which is the original matrix. All the dots of the stick figure is here. And then I have 3, 4, right? 3, 4. This is equal to 1, the 1 vector times 3, 4. Okay, so if we have 1, 1, 1, 1, 1, and here's 3, 1.4, notice the result is a multiple copy of it. We like having multiple copies. That means we're performing the same operation on every single point because we don't want to just move the head or the feet. We want to move the whole thing equally. And then the result will look something like this. And that should match this stick figure. Okay? So this is essentially how you do centering, right? You find the average, which we're going to call a C, center, and then you make multiple copy of it. And then you take X and subtract it away. Okay. So right this right here is right here. So now, um, this this is the center, right? We know the equation for center, which is this. So what happens if we plug this into the C, into the center term here? Well, if you plug them in, 1/7. So this will be like this. Okay. So that's where C transpose is. Now, 1/7, you can just move this out because this is a constant. So 1/7 is here. And this looks like this 1, 1, 1, 1, 1, 1, 1, 1. So this is the outer product. When you do this outer product, it becomes a matrix of all ones. Okay. So this is how I got one matrix 7 by 7. So I get a 7 by 7 matrix out of this. And notice this is the x term and this is x term. Interesting with matrix, you can actually pull them out. So the x just comes out right here. And what's left is this is the identity, the equivalent of a 1. So you can see when x times this is just equal to x because of identity. Now, once you have it in this form, we don't need the identity anymore, right? This one is just when this multiplied by this is just equal to x. So without this identity, we end up with this form. Notice it's just x times some matrix will automatically center the data. And we're going to call this matrix the centering matrix, which historically it's H. So H is going to do the centering. So there's actually a way which you just take X and multiply by some matrix, and it automatically moves the data to the center, like from the center to the center. Okay, so notice there are a whole bunch of points, 7 points. So just by multiplying those 7 points by this centering matrix, and the definition of centering matrix is that we have identity minus 1/7 of the one matrix. So that's it. This is the definition of centering. Okay, scaling the object, scaling the size. So the reason why we want to learn centering is because if you want to double the size of this, right? The easiest way is to move all the points to the center. And then once you have your triangle here, you just multiply everything by 2, and that will automatically expand it. So if you try to do just multiply all the points here by 2, it would not work because 3 would be 6. Let's see. So if you multiply all the points by 2, so 6, and it'd be 10. 6, 7, 8, 9, 10. So from 6 to 10. And then 1, 2, 3, 4. This will be 8. And this would be. This one would be 4, 8 by 2. 8 by 2. Oh, in this case, it actually worked. It is double the size. Well, in general, I'm pretty sure in general you can't do that. Yeah. Anyways, the idea is you want to move it to the center first. Anyways, so if you were to move to the center and multiply everything by 2, then it should work. So let's see. Let's say we have a triangle with points at. Yeah, so let's say we have this triangle. Now, following the definition of the centering matrix, then it's just 1, 3 by 3, right? All ones. And then you take 1/3 because you're averaging them. Now, if you were to calculate this out and multiply by this, it will automatically move the triangle to the center. So it goes to the center. Now, we next multiply the center by 2. So if we take all these values and multiply by 2, then it will automatically give you this triangle. And notice how this triangle is now double the size. So you can actually combine centering and double together, right? Scaling. So you multiply this and this together first, right? Then that will essentially um, allow us to perform this operation to the center and doubling all at once. So I should probably look into this more. Anyways, let's continue. So I want you to practice. Now is a point for you to pause the video. Basically, you have a stick figure, and this stick figure, you work for Disney, and you're modeling some character, and basically the character gets double the size, double in size. If he gets mad, I don't know, something happens. So what I just taught you is essentially how you move the stick figure to the center and then doubling it. But the part that's kind of complicated is once you're in the center and doubled, you want to move it back. So notice this person is standing at the point of 3, right? So this person expanded this way and expanded this way, but the center is still at 3. So let's see if you can write the transformation. Like pause the video, see if you can write the transformation. If you can, then you'll be able to like essentially make this person large and create the effect that a person is in, even though you actually move it, but you're going to create the effect that the person is just getting bigger. Okay, so your boss asks you to give him the transformation that will double the stick figure size in place so the stick figure still stands. Now, the second part of moving back is not easy. Like you will have to use everything you learn together just to move it back. So pause the video because I'm going to move on. Okay. So the first portion of the transformation is pretty easy. You multiply by the center matrix and then you multiply by 2, which allows you to essentially move the stick figure, right? The stick figure to the center. So these are the points once it's at the center and doubled. So center and double in size. So the next step is how do we move from here back out, right? Well, there are a couple of keys points to realize. One is that notice that the x location doesn't change. The person was standing at 3, and by the end, the person is still standing at 3. And the second point is that the y location is doubled. So previously, a person was this tall, but this location has doubled. So the y location of the center, so this is the center, right? That location has doubled. So what we need to know is to find the center average point for the original stick figure. So if we know this center point, like of this original stick figure, then whatever this point is, we keep the x-axis the same, and then we double the y-axis. Double. If we can do that, then we will essentially know how much we need to move this by. Okay? Well, to find the average point, it's not bad. We first find the average of each dimension. So remember, the way to find the average is through the one vector with some scaling. So by multiplying this, we find the average point. So the average point is 3 and 1.4. So 3 and 1.4. So the stick figure is around here. So that's how big the stick figure was. Okay, so now that we know the center, The next we want to do is double the second value. Remember, we're still standing at 3, but the y value is double to here. So we want to only make the x value the same, but double the y value. So the way we can do this is after is after we get the point, right? 3 and 1.4. So this is the middle point. We can multiply by this matrix. Notice this will keep the first value the same, and then the second value will get doubled. So this is 3 and 2.86. You can see that this is 3, and this point is 2. This point is roughly 2.86. Okay, we're going to call the scaling matrix S. So we're just going to call this S. And the equation becomes x times this. So this gives us the average. Once we have the average, we scale it by multiplying it by S. And when we do that, we get the location. We get the final location we want to move to. Okay, so similar as before, we want to copy this 7 times. So we multiply by a vector of ones. So whatever we have here, now we multiply by vector of ones. And by doing this, it allows us to copy it 7 times. So this is the final result. This right here is essentially how much you're supposed to move, copy 7 times. So if we take x, center it, and multiply by 2, and if we add this term we just talked about, which is we're shifting every single point for by 3 by 2, 1, 2.8. This is a typo. This is a typo. This is a typo. This should be 2.8. 2.8. Okay. So if we move everything by 3 and 2.8, which is around here, then we're going to move it back. Yeah, we're going to move it back. 3 and I don't know why I point here. It should be here. 2.8. 6. Yes, 2.9. So it's almost 3. So that's the center point. So that's the final equation. This part, you double the size. This part, you shift it back. And notice it basically used everything we learned. So in here, we were only working with 7 points. But in real life, well, there's a lot more points. But the idea is the same. When you want to transform an entire thing, you put them into a matrix format and then perform rotation, translation, whatever. Now, the point we are trying to get to right now is we're starting to form intuitions where certain matrix behave a certain way, and it allows us to view matrices almost as numbers that behaves like number. For example, we saw a matrix that behaves like 0, right? We saw a matrix that behaves like 1. We saw a matrix that scales the vector, that makes it longer. We also saw a matrix that allows you to rotate the vectors. All of these transformation is what starts allowing us to think of uh, matrix and vectors, how they behave kind of intuitively like numbers that we're used to. Now, there's one more matrix that's very special, that is the inverse of A, written as A inverse. It is basically, if we have 5 times 5 inverse, that gives us 1, right? Now, in the matrix format, then it's A times A inverse, and it will give us a 1, or the equivalent version of 1 in in the matrix, which is the identity. So this right here is the matrix inverse. Now, the matrix inverse is a continuation of treating vectors and matrices almost like numbers. So we can see that if A inverse times A should equal to identity, but it should also equal to A inverse, because both of them, inverse of each other, should produce a 1. Just like this here, should produce a 1. Now, the way you can find the inverse is through Gaussian elimination. So let's say we have a matrix A, right? Before, it was matrix A, like multiplied by some vector x. But now, instead of matrix A multiplied by some vector, we're going to multiply yet another matrix. And the idea is that if we multiply by this matrix, the output is the identity. So the augmented matrix then looks like this. You put the entire identity matrix here. So the way we would manipulate them is we would essentially perform Gaussian elimination. But instead of having one column here, we have to use both columns. So for example, over here, I have minus 2, right, plus minus 2 equation 2 plus equation 1. So 1, 2, 1, 0. So minus 2 equation 2. So 0 minus 2, 0 minus 2. So you put them together, it becomes 1, 0, 1 minus 2. Like right here, 1, 0, 1 minus 2. So notice on the left side, we have achieved the reduced row echelon form. So once we have done that, this right here is actually the A inverse. Okay? A inverse. You can always double check if your A inverse is actually correct. So if we have A times A inverse, and you will see that the final result is an identity matrix. Here's another example. Once again, over here, we have the matrix, and we can write it in the augmented matrix format, where over here is just the identity. And if you were to perform reduced row echelon form all the way, you will see that the final version is you end up with the identity here, and you over here becomes your inverse. So then this is the inverse matrix. Once again, you can just multiply by the original A matrix. If it's the correct inverse, you should be able to get identity back. Now, singular matrices are not invertible. There are some matrices you can't really invert them. They either when the problem has no solution or if it has infinite solutions. So the only way you can invert a matrix is if in the case when there's a unique solution. Okay? So the matrix, when you look at the singular matrix, when we talk about the singularity, we're talking about just this portion. We're not talking about the label. Okay? So this portion here, if we reduce down to the reduced row echelon form, and you got a row that's all zeros, then that's singular. Okay? You cannot take the inverse of a singular matrix. You can try it yourself. You can type it into NumPy. You will see that it will crash, and it just doesn't work. Special case. There's a special case where matrix is only 2 by 2. So if you have a matrix that's 2 by 2, then if you want to find the inverse, you take this, multiply it by this, AD, and then subtract this multiplied by this. So you will get this. And then you will switch the two. So AD like this, you put a negative on both sides, here and here, and that is the trick. So this right here, this equation here is allows you to just do 2 by 2s really quickly. You essentially find the difference between this and this, do a couple rotations, and you automatically get A inverse. Now, this is only for 2 by 2. Like other ones, then you have to go through the Gaussian elimination. Okay? So So remember, the goal is to get to identity. If you have identity, then that's good. That means it's inverse. So you remember from our last example, the answer was, what was the answer? The inverse was this, I believe. 1, negative 2, 0, 1. So 1, negative 2, 0, 1. Now let's use the shortcut. Notice if we use the shortcut, right, for this matrix. Yeah. Is that the shortcut? So yes. So this is a shortcut. So notice, well, you can flip them, but it doesn't matter. So the flipping doesn't matter. But we put negative here and here. So there's the negative. And over here, what we have is this times this and this times this. So it's just 1 times 1, 2 times 0. And once we have done this, notice that the answer is the same. So this was from Gaussian elimination we did before, and this one came from this trick. So you can, for a 2 by 2 matrix, 2 by 2. Other ones it won't work. Okay, so these are, yeah. So now we're gonna practice again. Try to see if you can solve them with Gaussian elimination. Once you do the Gaussian elimination, check 2 by 2 trick to see if these ones can be done. And then you can then also multiply them together. If you get A inverse A, you should be able to get identity. Now you can, lastly, you just use numpy to confirm your solution. Okay, so these are the solutions. Hopefully you guys are okay with them. Now, it is interesting. Now that we understand the concept of inverse, if we go back and look at the problem, this was the linear system, if you remember, where we have a matrix times x is equal to y, and we're trying to find x. This means that if we multiply, by knowing the concept of inverse, by multiplying inverse on both sides, this right here becomes identity, because a times a inverse is just identity. But x times identity is just x itself. Therefore, the solution of the linear system that we have been solving is just A inverse times Y. So if you know the inverse, you can very quickly just multiply them together and you get the solution. So this is why it's useful. You can now look at complicated, well, this one is not so complicated, but you could look at complicated variables and essentially solve for x. Okay. All right. So for this lecture, the identity matrix is called I, EYE. And if you put a 2 here, it's a 2 by 2 identity. All right. Now, if we do A, so A is identity, A dot X. X times identity is just itself. So you can see that it's the same thing, this and this. The way you can find inverse is through linear algebra library. You just type in INV right here. So the other vector you want to learn is called ones. So you can create a 3 by 3 matrix of ones this way. Or you can create a 2 by 3 matrix of zeros. So these are how you would do this. All right, so this is the final practice. The goal is for you to essentially take A, right, and y1, y2. Let's say we have an equation where ax1 is equal to y1, ax2 is equal to y2. Now, solve by hand the inverse of A. Right? See if you can solve the inverse of A. And then what you want to do is multiply A inverse to see if you get an identity matrix. So that will help confirm if the inverse you got is correct. After this exercise, you want to find x1 and x2, right? So you want to solve for it. But instead of solving it using Gaussian elimination, which we have been doing, you want to multiply by the inverse. So take y1 and multiply by the inverse, and that will give you x1. And then you take y2, and that will give you x2. Now, finally, use numpy to verify the solution. Okay, so this is it. The solution for x1 and x2 is here. And yeah, then make sure you take a look and that you can solve this problem. All right, good luck.